I'm going to wait until 5 after 1. Some people are still showing up here at the classroom. Give them a little bit of time to roll in. Did you guys get to sign in at the front desk? Cool. Thank you. Okay, I think it's 5 after. I think most of the people that are going to show up we've got here. So if you were here for the first session, I think a lot of you were. We just talked about some of the basics of multi-core programming and multi-core hardware, specifically in the context of our Stampede KNL extension. Today, which is not the 27th of January, if you're paying attention, it's the 3rd of February. I'm going to talk a bit about how to actually optimize your code in a way that enhances and promotes vectorization and also leads to better multitasking. Some of these topics will overlap with what I talked about in the previous section, but I'll go in a little bit more detail in this one. So what I like to think of is 3 very general rules for optimization, and these rules apply to whether you're optimizing serial code, vectorized code, or your multi-threaded code. Is you really want to work hard to make sure that the compute-intensive parts of your code, the part of the code where you're spending most of your time, is really clean. And what I mean by clean is simple, linear, predictable data structures. You want to save like all the cool object-oriented methods for staging and managing your workflow. That gets in the way of the optimizations the compiler is able to do for you automatically. So if you set up your code in a predictable, the compute-intensive parts in a predictable, clean way, the compiler will actually do a lot of the heavy lifting for you in terms of making your code actually run faster. There's two main approaches then to two additional components of this. You want to use optimization flags, and these kind of give the compiler a sense of how hard it needs to work. And it also tells the compiler what instructions are allowed. So in the last section, we talked about all the different vector instructions possible, AVX, AVX2, etc. These flags tell the compiler what instructions it's allowed to use. And as I mentioned as well before, the math libraries that are out there you want to take advantage of. People have worked a lot of time to make these run well. As you saw in the lab this morning, they can actually do threading for you automatically. It's pretty great. And improve the performance of what appears to you to be a serial code suddenly becomes a threaded code just by using these libraries. And like I said this morning, these are specialized for particular architectures. They'll run optimally, whether you're on a Sandy Bridge node like our Stampede system has, or a Knights Landing node like our KNL system has. I also talked about this morning, but generally approaches to vectorization from worst to best is assembly is not great. It's extremely hard to do. It's not going to be that fast probably. If you write code in assembly that uses instructions that one processor can use but another can't, it won't be portable at all. Intrinsics are better. Intrinsics are extensions to programming languages that are pretty close to assembly, but they save you some of the hard work and help to ensure that you're writing correct code. What's typically the best approach is to use just let the compiler vectorize for you. It results in extremely portable code. You just have to use the appropriate flags for the hardware that you're running on. And in the end, it automatically vectorizes your code, assuming that you've written your code in a way that promotes this vectorization. And we'll talk about what that means in a little bit here. And then the best you can really do is if you've linked to optimized vectorized libraries. So most of your programming opportunities will be in loops. Keep the loops simple, like I've been saying. You can evaluate compiler output. So there's different flags that you can pass the Intel compiler in particular, and it'll tell you things like the different optimization steps that it took, if it vectorized certain parts of your code, etc. You want to consider your memory access patterns. Unit stride is good, and I think I talk about that for a bit in a couple of slides here. And then, of course, take advantage of the math libraries that are vectorized and available for you. In particular, the math kernel library is Intel's math library. If you were to use, for example, the Python builds that we use on our systems, that we've built on our systems, you will be getting the benefits and the performance improvement that this library provides. And same is true as if you use the MKL in your C code or your Fortran code, et cetera. You can get that multi-threading and vectorized performance for free. Different ways to induce vectorization or the specifically done by compiler flags. So Intel and GCC are kind of the two main compilers that we support here at TAC. Intel, its default optimization level is 2. If you weren't here this morning, optimization levels range from 0 to 3, with 0 being the least optimized, really not optimized at all, up to 3, which is the most heavily optimized. And at this optimization level, the Intel compiler will give you SSE level vectorized instructions. And if you recall from this morning, those are instructions that are operating on 2 double precision data elements simultaneously, 2 64-bit data elements simultaneously. If you pass the Intel compiler the -x host flag, it'll give you the most advanced instructions that are available on a given architecture. And then you can also specify individual levels of instruction sets to use: AVX, AVX2, like AVX 512. As you might have seen in the lab this morning, this can come into play when you're compiling on one architecture, but actually want to run your code on another architecture. GCC has a very similar setup, but vectorization does not kick in for it until you get up to optimization level 3. You can get the most advanced optimization level using marchitecture=native flag with the compiler. And then it also has corresponding vectorization flags that Intel does. So MAVX instead of XAVX, not that big of a difference. AVX2. The bigger difference is when you try to use the 512 instructions, the AVX 512 instructions for the mic, you actually have to pass 4 different compiler flags to GCC. I don't know what the reason for this is, but each one of these represents different instruction sets. And if you pass all 4 of these, that is equivalent to just passing Intel the mic-AVX 512 flag. So how do we actually get loop vectorization? So most vectorization opportunities occur in loops. It's very true. Some of the characteristics that are required in order for the compiler to automatically vectorize a loop for you is that the loop must be countable. And what that means is the number of iterations has to be known before the loop executes. You can't have some kind of conditional termination like a break statement in there or something like that. The compiler will see that and not know what to do with it. You also have to have what's considered a single flow control. There has to be a single path through your code. You can't have like switch statements in there. That will confuse the compiler and prevent vectorization. And then you can have actually if statements in there, but they have to be just kind of straightforward if-else statements. If you start having like nested if statements or something, you're not going to be able to achieve vectorization. Something to note is that only the innermost loop is ever going to be vectorized. Another important thing which can arise a lot is no function calls are allowed in loops that you want to have vectorized. You can step around this, and we'll go through how this is done just by inlining those function calls. But that would basically, you don't want to have any function calls if you can avoid it. And then you want to just have a single level of a function call otherwise. You don't want to have functions calling functions calling functions. That's what I meant earlier when I'm saying avoid object-oriented programming type approaches in these compute-intensive parts of your code. And finally, no loop dependencies. And what is a loop dependency? Vectorization is really changing the order of your computation from if it was happening in a sequential fashion. The compiler wants to vectorize your code if you give it the right flags, but it's extremely conservative and careful to make sure that it doesn't cause incorrect results in your code by maybe violating or not taking some of these dependencies into account. And so what it does is it performs a dependency analysis. This analysis does take into account the actual width of your vectors. If you're only vectorizing over 4 data elements and your dependencies are 5 data elements apart, then it's not a problem. And you'll see what I mean by this, I think on the next slide or two. The compiler actually performs a cost analysis, a cost-benefit analysis to to generating vectorized code. This is because it's not always faster to vectorize code. If your code is set up such that there are possible dependencies in the code, the compiler can actually set up different branches in your code that it will take based on checks that it does at runtime to see, it can check for you if there's a dependency there. And because you've got suddenly additional branches, there's additional logic that's required to get through that part of your code, and it can generate an overhead. And finally, short loops aren't always worth it. If you're only looping over 2 or 3 elements or anything less than 10, typically, it seems like, from what I've seen, that it's not really worth it to do the vectorization. There's some overhead associated with it. So let me just describe a little bit about dependencies and how you can pick them out. The first type of dependency is a read after write dependency. And the idea is you write a variable in an earlier iteration, and in a later iteration, you need to read that variable. This is not vectorizable. I'll show you a short example what happens if you were to vectorize this code. This loop here, this for loop that I showed here, is an example of a read after write dependency. In the first iteration, A of I is being written to, and then in the very next iteration, that particular data element needs to be read from. So they're dependent on each other. Each iteration is dependent on the next. The next example that we have is a write after read dependency. The idea here is just that the variable gets written to, and then read from. The variable is read in an earlier iteration and written to a later iteration. This is actually vectorizable, and we'll work out why that's the case. And one thing to note, Intel's tools would call the first dependency a flow dependency, and this second write after read dependency an anti-flow dependency. The last 2 types of dependencies are read after read. So this isn't really a dependency, you're just reading a variable in multiple iterations. There's nothing, you're not breaking anything by reading the variable. You're just reading it, you're not changing its value. And then a write after write dependency is an example of this is in this for loop down here. The same variable is being written to in different iterations. You can imagine that if iterations were being performed simultaneously, like in the case of vectorization, that it's unpredictable which value A will be updated with. So it's a little bit confusing sometimes to think about when you have a dependency and when you don't, but I can just show you like a fairly quick and easy way to do some dependency analysis. People have like fancy dependency graphs and stuff that they come up with, but hopefully, you won't need those kinds of methods. So let's do a quick dependency analysis for this for loop up here. A of I minus 1 times B of I is equal to A of I. Okay, let's say I'm vectorizing over 4 elements. So you're doing 4 operations simultaneously. And I have my 4 iterations written out here. So my first iteration will have A of 2 equal A of 1 times B of 2, and so on. The vector operations occur. What happens is all at once, B of 2 through 5 will be loaded into your vector register. A of 1 through 4 will be loaded into your vector register. And then they will be combined all simultaneously to A of 2 through 5 in a different vector register. So if we just think of a simple example, where we can compare the results of doing this sequentially or in a vectorized fashion. Let's say I have two arrays, A and B. All of the values in A at the start are going to be 1. All of the values in B at the start are going to be 2. Now let's just look at these iterations starting in sequential mode. So iteration 1, I just have 2 times 1 is equal to 2. Now I need this A of 2 in iteration 2, which value is updated in iteration 1 to 2. And then I have 2 times 2 equals 4. And then so on. 4 times 2 equals 8 in iteration 3. Then I use the results of that iteration in my next iteration. 8 times 2 is equal to 16. Now I can think about what if I did this in vectorized mode, where I load up all of my A's, which all start out at 1, remember, and all of my B's, which all start out at 2, and then I do them all simultaneously. They're all going to have the same value, 2. So we can compare the sequential version versus the vectorized version and see, okay, these are different. This is not going to vectorize. And so sometimes that's a nice way to do dependency analysis. Just write out a few iterations, wrap your head around it. So let's do the same thing for right after read. If you recall, I said this is vectorizable, but why is that the case? I'm going to consider this for loop A of I equal to A of I plus 1 times B of I. Just like before, A of 2 through 5 gets loaded all at once by a vector instruction. B of 1 through 4 gets loaded all at once. They all get multiplied simultaneously and then stored in A of 1 through 4. If I use my same example as before, in my sequential mode, all of my A's start out as 1, all of my B's start out as 2, and I can go through and perform iteration 1 is just going to be 1 times 2 is equal to A of 1. Iteration 2 will just be 1 times 2 is equal to 2, and so on. So you can see I end up with 2's in all of the array elements of A, all of the elements of A. Now if I did this in a vectorized fashion, I first load up all my elements, all 4 elements of A, and all 4 elements of B, multiply them together, and boom. All my, I get my results for A, and they are all 2, just like in the case of sequential. So I've worked out that, okay, there's no real dependency violation occurring in a read after write. And you can certainly do that for the read after reads and write after writes and see what happens. So I want to talk a little bit about striding and cache reuse. Striding is going to be the distance between the data elements that are accessed in memory. So let's think of arrays. A and B, you would call a unit stride or a stride of 1, is this top loop here. And that's accessing each element sequentially in the array. Stride of 2 is if I was accessing every other element. So in the second row, my for loop has an incrementation value of 2. So I'm accessing every other element in these arrays. And then so on with the stride of 4. Thing is, whole cache lines, and a cache line is typically 8 double precision data elements. So, 8 doubles in C. 8 whole cache lines are always moved from memory to the cache. If you might be familiar with the idea that it's much slower to move data from memory to cache than it is to move data from cache to the cores. Think almost a factor of 100. Now, if you are using a unit stride, you're using each of those 8 elements that you've brought into the cache. If you use more than a unit stride, then you are only using like some, fraction of those elements that you brought to the cache. Yeah, and the effect is going to be greatest when you're pulling data in from memory, as opposed to if it all fit in the L1 cache. This doesn't really have that much of an effect on you anymore. So in the previous section this morning, I talked about memory hierarchy, but let me just mention it again. Down at the bottom diagram here, we have our core all the way on the left. The L1 or level 1 cache is closest to the core. It requires the least latency, I think something like 4 cycles to get at the data in the L1. Then the L2 is a little bit further out. The latency is a little bit higher. It's harder to pull the data in, or it takes longer to pull the data into the core. And then all the way on the end, way out there, we've got our memory, which is so there's about a factor of 10 difference in the bandwidth between the L1 cache and the memory, and almost a factor of 100 difference in the latency. So let's think about another way that striding, you can think about striding. So I'm going to compare, describe how Fortran two-dimensional arrays are laid out in memory. On the left here, what we have is, let's say we have 3 data elements can fit in our cache at one time. It's just a toy example. And then we have our columns of our 2D matrix in Fortran in this square here with the red, the green, and the blue. If you lay these out in memory, memory is going to be contiguous, and so what it looks like is this line along the bottom here. We have our first row, or our first column in red, and after that comes our second column in green, and then after that comes our third column in blue. Now, if I am, there's a couple of 2 different approaches or problems with this here that could arise. Let's say I was accessing the data row-wise here, and my data is arranged column-wise in memory. So what would have to happen is first these 3 data points would have to be moved from memory into cache. I would take 0, 0 out of that and use it. Then I'd have to write that back out and then pull the second column of memory into cache. I could only use 1 element from that. I'd have to write that back out. And then the third time pull that in and then write that back out. This has just cost me 3 memory accesses. That's not a good thing. But like I said, it's about 100 times faster to get the data from the L1 cache. But if I had accessed it, so that'll take 9 accesses total if you work it out. But if I access it along columns, as shown in this do loop, a nested do loop down here, I would bring in the first, all 3 in red into the cache, operate on all of them, boom, done. Then take all the green into the cache, operate on all of them, done. And then take the blue here and operate on all of them. So that would only take 3 memory accesses. So I've just saved myself 6 memory accesses, which is about think of it as one of the most expensive things that you can be doing when you're computing. C is actually a little bit worse than this, or sorry, C is actually a little bit different than this. It is arranged along for 2-dimensional arrays, row-wise first. It's called row ordered versus column ordered. So you can see the red goes along the row. Those are the first elements in memory. Then the green is the second row. Those are the next elements in memory. And the blue is the third row. And the last elements in memory. And so actually, you want to be accessing the outer dimension when you are going through two-dimensional arrays in C faster than the inner dimensions. Fortran is just the opposite. This is something to really watch out for, especially in the case of multiprocessing where memory bandwidth is such a scarce resource. You have so many cores making so many demands on the memory, you really want to be using the data that you pull in to your memory as effectively as possible. So I would say striding becomes even much more important as we go into the world of Manycore. So effectively what happens, if your data is in memory and you pull it into the core is basically operating on it instantly compared to how long it takes to go out and reach the memory and pull it in. So when you go to a stride of 2, you look at this little plot in the your upper right here. If I double my stride along the x-axis of that plot, my time to solution actually doubles because basically it's just taking me, I'm getting half the data into the core that I need to operate on when I'm using a stride of 2. When I use a stride of 4, it's 4 times worse. When I use a stride of 8, it's almost 8 times worse. Striding through the L2 and the L1 is not quite as bad because it can get at the data a little bit faster. It can overlap some of the loads with the operations that it's performing. It's still not good. In particular, you can imagine when you are working on vector registers and you are not using every element that you are loading from your cache into the vector register. Let's say I'm using a stride of 2 and I move 4 double precision data elements into my vector register. With that stride of 2, I'm only using 2 of those data elements when I perform a vector operation. Now, there's different ways that you could think about this happening. It might be the case that you actually just do 2 loads instead of 1 load. And that's probably the more accurate way to think about it. But those loads cost time. There are additional instructions that are not instructions spent executing your code. A very closely related topic to the concern I just brought up about striding in a vectorized setting is data objects can be created in memory on specific byte boundaries, and this can increase the efficiency of your loads and your stores. A vector load is only accessing from a single cache line at a time. I don't understand exactly why that has to be the case, but that is the case. A vector load is only pulling from one cache line at a time. For what this means is that you want your loads to fit in an integer, an integer fashion, to divide evenly into the size of the cache lines. Because the cache line is 64 bytes for something like AVX or AVX2, where I'm loading 32 bytes simultaneously, I want them to line up on 32 byte boundaries in the code. And I'll show you a schematic of this on the next slide. For AVX512, you want the alignment to be along 64 byte boundaries. And what this would allow is that a single load is moving 8 data elements simultaneously into your vector registers. Now you don't have to worry about this so much because the compiler can actually detect a lack of alignment. It's pretty great. And then it can peel off iterations in your loops, for example, to make sure that the bulk of your loop is aligned. And maybe there's just some small part of your loop that's not. There's some overhead associated with performing this peeling operation. But it's typically not, I would not say, a first order effect by any means. You can also, within your code, use, there's system calls such as memoline, or C functions such as memoline that'll make sure, I think POSIX memoline is another name. You can align your data along different byte boundaries. And you can use this as an alternative to malloc, for example. And so you can malloc blocks of memory that are byte aligned. So what would happen in vector loads ideally is if our cache lines were holding 4 data elements, I have my 4 cache lines in blue, yellow, brown, and red up here. A single access to cache would be able to load 32 bytes of 4 double precision words simultaneously in one load. Then I go on to cache line 1, do a load, cache line 2, do a load, cache line 3, do a load. So I only need to do 4 loads there. How it looks like if the data is unaligned is on the bottom here. The gray squares are just empty parts of the cache. And then my data element starts on the third block of cache line 0. Unfortunately, it spreads out into cache line 1. And so what has to happen is the processor has to do a load from cache line 0, then it has to do a load from cache line 1, and then it has that whole, those 4 words. So it took 2 loads to do move the same amount of data that the aligned loads in the top were able to do in 1. And so you can see this continues down the line, and it ends up being double the amount of effort in order to load this data into the vector registers. This can also show up when you are working with multiple dimensions arrays, and it can be corrected by something called padding. So if I consider a 4x3 array in C up at the top here, my first 3 data elements are in blue, that's for the first row. The next row's 3 data elements are in yellow, and so on. You can see that I'm going to be doing unaligned loads all the time. I'm going to have to pull the 3 blue elements, then I'm going to have to pull 1 of the yellow, then I'll have to do another load for the rest of the yellow, and so on. What you can do is just add a final element to your, an additional row to your array, column, and then make sure that then it will align as it does along the bottom here. And basically what you do is just not use that last, the operations that you have in that last, row. Okay, so you can see a really big effect on performance with inlining. Inlining has a couple of effects, but one of them is it can enable vectorization. So functions within a loop, like I said before, prevent vectorization. I mean, think about if you're a compiler and you come across some function in a loop and you want to vectorize this loop, like, you don't know what that function does. You can't test for dependencies. You don't know what's going on there. So it's just not going to do anything. Now you can overcome this using inlining. So if a function call and its definition are in the same file, you can use the flag in Intel -IP or -03, the last level, or the highest level optimization. We'll give you in file, same file, inlining. If the function call and the definition are in separate files, then you actually have to give it this -IPO, interprocedural optimization flag. And that'll be, that'll take care of cases where, you know, your function is called in your main source file, but it's actually defined in a separate source file, as it's very common, right? Let's just see an example of what inlining looks like. On the left here, I have before inlining, I have my function defined R2. It may or may not be in the same source file as the main function where it gets called. Not worrying about that at the moment. And then down in this loop here, you can see that function getting called over and over again. How would you vectorize that? I don't really know. If I was a compiler, I wouldn't know what to do. But after inlining, it just inserts the value for that, the lines of code for that function directly into the code. So it actually does this at like a pre-compilation phase. It sticks that line in, it sees that, then it can do its vector analysis on that. It knows how to work with that. Just to kind of give you a sense of, this is just a generic timing. I don't even remember exactly where it's from, but it's inline. If your code is inlined, or a particular function is inlined, and if it's been vectorized, and the time that it takes for it to complete. So with no inlining and no vectorization, it's about 1.5 milliseconds. If I add inlining, you actually get a really big improvement down to 0.44 milliseconds. And if I throw in vectorization on top of that, even better, about a factor of 8 improvement, adding the vectorization, and overall, huge factor of 30 improvement over the normal, over the original operation. So I think the last topic for vectorization that I'll be talking about is aliasing. Aliasing is this idea that two different pointers, you really only run into this in C, you don't run into it in Fortran, but it's this idea that two different pointers can be pointing to the same array or to different elements in the same, or to, yeah, different elements in the same array. Loops and routines that use pointer references might not vectorize. The compiler wants to be absolutely sure that no dependencies are being introduced. So when you're passing, in functions that are accepting pointers, when you're passing pointers to them, ensure that the compiler can detect when the references actually overlap. So here's an example of a function which accepts references as its arguments. These references reference arrays. Function is my copy. We pass it the size of the arrays, and then the pointer to those arrays, and we do something here. Based on what I just said, this last loop here, the compiler might not recognize because there might be hidden dependencies. One element of A might be pointing to a different element of B. The compiler just does not know. They could be quote unquote aliased. But the compiler will actually, for a simple case like this, test for overlap at runtime. So what you can think of it as doing is making two different branches, like something like an if-else statement shown here. The top one, the if part, is if these arrays overlap in any way, do not vectorize this, perform it sequentially. If they, however, they do not overlap in any way, then we'll unroll the loop and vectorize the thing, and it'll be great. Now, that's great that the compiler does that for us. It does actually introduce some overhead to when it does that, which can impact your performance. And additionally, if the overlap test that it would have to perform becomes too expensive, and now it has some heuristic in there that determines the cost of performing these tests and the benefits that it would get out of the possible vectorization. It might decide in a loop like this, where we've now added this offset, which is a pointer to an integer, might decide that the test it would have to do here is not cost effective. There might be too many if-else thens and whatnot for it to be worth it to do it. Something that you could do in a case like this that would fix that immediately is using this ANSI alias flag. And basically what that says is we're going to follow the ANSI standard. Types, different pointers of different types will not alias each other. And so you're promising the compiler that, hey, this is safe here, don't worry about it. You can build the test. You don't have to worry about this additional pointer to the integer I off. Another thing that you can do, which is nice, so you can just tell the compiler for each loop kind of like the status of the safety of vectorizing it, or how hard it should work to vectorize it. So there's these 4 different pragmas here, which you would just put immediately above the loop that you're interested in vectorizing. The first pragma is IVDEP, and that just means it doesn't assume any dependencies. So like in the previous case where maybe we have some kind of aliasing or something, it's not going to assume that those are aliased. It'll vectorize if it can't prove that there's a dependency, like a read after write, or for example. That would be a dependency that it would not try to avoid, or that would prevent it from vectorizing. Vectorize always is just vectorize if there's no assumed or proven dependencies like usual, but ignore how much it costs to do the vectorization. No vector pragma is just never vectorize. And then pragma simd is always vectorize. No matter what loop you throw this at, it's going to vectorize it. So you could definitely run into the case where you break your code and get wrong answers if you aren't absolutely sure that this is safe to use. So just a quick summary. We're rolling in the KNLs. They have these 512-bit width processors. They're capable of 16 simultaneous flops per core. The wider registers that they have, though, are not going to guarantee you performance. You need to make sure that your code's vectorizing, and we'll talk about how you do that later on and in the labs. You want to ensure that there's no, in order to get vectorization, you want to ensure there's no explicit dependencies. Make sure there's no functions. That's a pretty easy one, right? We can all do that. And then ensure that there's no aliasing occurring. So with that, I'm going to take a 10-minute break. And then we'll talk about optimization approaches and good rules of thumb to use when we're multi-threading or multi-processing. I think there's coffee out there now if anybody wants some. I know I'm going to grab some.
Yeah, the compiler unrolls the loop for inlining until utilizing the maximum length for the vector.
Yeah, and in fact, we can use, we won't always use the maximum length of the vector. Sometimes it makes more sense to use a slightly smaller length of the vector, like 2 or 4 instead of 8. But it will try to use the maximum if it's possible and if it's cost effective. Yeah.
And regarding the stride, so 8 stride has like a 1/8 utilization for memory bandwidth.
Yeah.
Well, what about 9? 9 would be better than 8, right?
So what happens when you go to 9 is you're already only using, each cache line has 8 elements on it, right?
Right.
Once you go to 9, you're already only using 1 element from each cache line. Or once you're at 8, once you go to 9, you're still only using 1 element from each cache line.
Right, but that may be only cached in the previous access to memory.
It's possible, yeah, definitely. Yeah. I think it would be hard to predict ahead of time, except for maybe very simple case where you can control that. But yeah, it could be the case, sure.
And regarding the pragma thing, what's the default? So if we don't use any pragma, then this.
So it will make sure there's no assumed dependencies, we'll make sure there's no real dependencies and proven dependencies, and it will do a cost and benefit analysis to decide if it's worth it.
The pragma prioritizes it so that if you put the pragma, it's like, oh, I should do this one first before I do any. It really comes down to resources for the compiler. At some point, it becomes a memory issue. Because the more it has to keep track of, the bigger memory capacity.
Could you also use the restrict keyword?
Yes, yeah, that's just a topic that I didn't get to, unfortunately, but absolutely, that's probably one that needs to be in there. Is have the restrict keyword, and then I think you have to throw a restrict flag. Also, when you do the compilation for that to be observed.
Is there a restrict it's not part of the sequence.
I do not know. I do not know about that. Actually, I've been in C land for a while. I'm not up to date on my C++. I used to be pretty good with that. Voice is worse, but we've got 1 more hour. Next.
And regarding the padding, actually you should use the padding size if you use like a size of array, or if it's like internal padding, user still thinks the not padding.
No, so they're the
Size of would actually, that would work too, because that would make sure that
this is
your data, well, you have to, so that was in the context of 2-dimensional arrays, right? So you would have to make sure that each, like if you're working in C, each row was the right size. So if you did a malloc along the rows, yeah, you'd have to make sure that they are lining up on the right, that they are the correct size. So you could be using just the first 4 or you could be using just the first 7 out of 8 columns. from that malloc and say size up. This row is going to be 8. Some like 8 data elements. This row is going to be 8 data elements within your malloc, and then only use the first 7 elements in your calculation. And that should get you really good aligned effect. They'll have the same effect as the hash.
So normally user has some responsibility for aligning.
Yeah. So the alignment itself is not so bad anymore. It used to be really bad on the Knight's Corner processor, which is the one that came before Knight's Landing, because actually, okay, you have to do more loads when it's on the line, right? That's bad. But it was actually much slower at doing the unaligned loads on top of it. So you could actually make a lot of mistakes. Now, compilers peeling away parts of the loop such that you start a line. I would say it's a very small effect that you don't have to worry about. The only time that you're going to run into it is maybe if you have small arrays like that that don't fit evenly, don't line up evenly in the cache.
Yeah, when we allocate the array of struct, then each struct also headed to should be.
It's easier to do correctly struct arrays on access because those get lined up in memory. An array of structs, if you're not using every single element in that struct, then you're striding.
Right. For a single object. So probably not good. So you may compiler may do some adding
Yeah, I don't know if it was bad for you or not. An array of structs. I'm not sure.
I mean, so actually the question is how much stuff it
I would think not.
right? So you put like
Destructive arrays is always better than array of structs. You use more of the data that's in there.
these numbers are really, but I don't know if it really say us anything.
Okay, I'm going to get started with this next section here, where we're going to focus more on performance considerations in the context of multitasking. If you're lucky enough to be here this morning, you have seen this slide already, and these are just some of the basic concepts associated with multitasking. Multiprocessing is just the case where tasks are processes. Each task has its own address space, its own private data, if you like. Multi-threading is just tasks or threads within a process. Tasks share address space or can share data. Two metrics for measuring how well you are parallelizing your code are speed up and efficiency. Simple, basic metrics, very intuitive. Speed up is just the runtime of your parallel code versus the serial code. Efficiency is the speed up relative to the total number of tasks. It's really like how much parallelism are you getting out of each task that you throw at the problem. If it's perfect, it'd be 1. Process and memory affinity, we talked quite a bit about earlier this morning. It's the idea of associating tasks with physical or logical cores and with different nodes in memory, what they call Newman nodes. There's this issue of contention for shared resources. Basically, you have limited bandwidth to your cache and your memory. Your interconnect can only push so much through it. Dependencies that arise in multitasking are actually very similar to the issues that you see with vectorization. The catch here is that the compiler doesn't save you from dependencies in the case of in these situations. So you can actually end up with wrong code parallelizing parts of it without being careful about dependencies. And then the final concept is this idea of granularity, which is the amount of work per task. It's important to balance granularity to get parallel efficiency. Too much granularity can lead to load imbalances. Basically, some tasks could be idle for a really long time waiting for other ones to complete. Too little granularity can lead to large overheads. This parallelization isn't free. It costs time and cycles to partition the problem, to assign work to tasks, to communicate data between the tasks if they need to do that, and to coordinate tasks, deciding who gets to go when, who gets access to this data object at what time. I apologize to folks that have already seen this slide and maybe this next one this morning. But we do have some folks that weren't there this morning. So just an easy example of load imbalance is, say we have a loop with 10 iterations. It's divided among 9 threads. Each iteration takes a single thread a single day. Let's say 9 iterations are done the first day by 9 threads. And then you still have that last iteration that needs to be done the second day by 1 thread. So 8 threads are idle for that entire day. There's negligible communication overhead, but there's really poor load balance. If I had just used 10 threads, this would have been done in a single day, this workload, instead of 2 days. Example of parallel overhead is a loop with 10 iterations divided amongst 10 different threads. Let's say the setup of this parallelization takes an entire millisecond. But let's say it only takes each iteration or each thread 0.1 milliseconds to do their job. 10 iterations are done by 10 threads. And actually that should be 2 milliseconds. Or yeah, so the total parallel time is 2 milliseconds, whereas the serial run would have only been a single millisecond. So we've clearly not gained by parallelizing our code there. So there's different modifications that you can go to loops, do to loops in order to provide opportunities for this type of parallelism, and also to improve things like load balancing and reduce overhead. I'm focusing on loops because loops are often, just as in the case of vectorization, where parallelism can be realized. Basic idea is divide the iterations among your tasks. You need each iteration to be independent. They can't be depending on each other because they're not being performed in any predictable order. Now you can remove or make it such that these iterations are dependent through different loop modifications. And as I mentioned before, you can improve your granularity or your load balancing and reduce your overhead through some of these modifications. So just a general good rule of thumb for good loop granularity is you want to parallelize over loops that have a lot of iterations compared to the number of threads that you have. Basically, the idea is the overhead is going to be less significant because there's a lot of iterations. The time to set up versus the time actually spent working is going to be relatively small. And load imbalance is going to be less of a problem. So if you have if you have like extra iterations, it's going to be a lot versus the time all the threads are working, it's going to be relatively small as well. So let's look at an example where we can remove a dependency. So this particular loop at the top here, a of j equals b of j minus 1, b of j plus is plus equal to 1, incremented each iteration. Later iterations in this loop need results from an earlier iteration. The next iteration needs a result from the previous iteration, and this is a dependency. It's kind of a unnecessary dependency, though, because we can do what's they call loop fission. I don't know why they give these fancy names to these things, but they break up the loop into two different steps such that now they can both be parallelized. So now we've broken the loop at the top, separating each of those statements out, given them their own loop, and now these are clearly safe to parallelize. I parallelize the first loop. I can throw however many, break that up any way I want. The answer is going to be the same. And then the second loop, likewise. Okay, now the opposite of that is loop fusion. This lets you increase granularity. You add additional work to each iteration in your loop. What it's doing is reducing your loop overhead relative to the amount of work each one of your tasks is performing. So let's say I've got these first two loops here. A of j equals d of j times c of j. In the second loop, d of j equals e of j times f of j. These guys are completely independent of each other. Why not just combine these two loops? And this way I'm giving more work to each task. Whereas before, at the top, if I wanted to parallelize that, I would have had to parallelize the first for loop and the second for loop. So I'm removing half the overhead by combining those loops into one, as I have on the bottom. Okay, another thing that you might consider doing, merging nested loops to increase the iteration counts. And what this results in is better load balancing. So imagine I parallelized the top for loop for I is equal to 0, I less than n, blah, blah, blah. Each one of the tasks will get some portion of that loop, but they're going to have to do the entire nested loop, the entire loop over j. That's not broken up in any way amongst the tasks. So if it takes one task much longer to do its portion of that work than another task, you're going to end up with load imbalance. If I combine these loops, as shown in the bottom here, then I'm just parallelizing over the for loop, and each the tasks are going to be broken up in a more even fashion amongst the work is going to be broken up in a more even fashion amongst the tasks. Now, this is especially going to be relevant when we consider some of the scheduling options that you're given, for example, in OpenMP, where you can say, you can dynamically hand out work to tasks as they complete the initially assigned work. So load balancing with OpenMP. Again, OpenMP is kind of like the most common paradigm that we have right now for doing multitasking, or in the context of OpenMP, it's called multi-threading. OpenMP has, when you want to parallelize, hopefully most of you are at least familiar with this pragma statement up here, pragma OMP parallel for. You put that above a for loop with OpenMP, it'll parallelize that loop for you. You can give it this additional modifier, the schedule function, and that'll determine how work gets divided and handed out to the tasks that are part of that loop. So there's three different options to give the schedule attribute. A static, this is just the default scheduler. Basically, it just divides up all the iterations into the number by the number of threads that you have and hands out the work. It has almost no overhead. It can actually do that step at compile time. But it also has no load balancing, right? Like, I've broken up the work. If none of my tasks finish and one of them's still going, those other tasks are just going to sit idle. An improvement upon that is dynamic, where you actually are assigning work to tasks. So if none of your tasks finish and one of them still has work to do, this dynamic setting will actually toss some of that work to your idle tasks. So it'll balance out the work. It's doing load balancing for you. There's some overhead here because occasionally the runtime of OpenMP has to go and check and see, do we have anybody idle? How can I balance these tasks better, etc. Guided is kind of similar to dynamic. It's kind of the odd duck of these two. Basically, it initially starts by handing out large chunks of iterations to tasks like dynamic, and then it just kind of gradually reduces the size of these chunks to minimize the chunk size. The idea is that sometimes it might have less overhead than dynamic. I have never found a case where guided really improved my performance over dynamic, but you know, maybe some people do. One thing that seems almost like magic that I wanted to mention while we're talking about performance increasement is the idea of a superlinear speed up and also slowdowns that might seem like your code is just running slower. Speed up, superlinear speed up is when the speed up that you get is exceeding the number of cores, additional cores or resources that you're throwing at the problem. Your efficiency is more than 100%. Like, how can this happen? It can happen if you have decomposed all of the parts of your problem small enough that it just fits in each core's cache. So now suddenly you don't have to make accesses to memory anymore. Everything's coming out of cache. And so your code just like suddenly jumps up in speed. Basically, the idea is the serial problem didn't fit in the cache. It could be streamed into memory and back out all these times. But once you break it up small enough, throw enough cores at the problem, the whole thing fits into cache. You're getting great cache line reuse. So the moral of the story is that you want to be careful if you're profiling or testing the performance of your code using data sets that are too small. So it might not be representative of the speed up or efficiency that you see with the real world data set. On the flip side of this, when you're going from these small data sets, but you increase the size, and then you increase the size of those data sets, you're going to be seeing the opposite problem. And it might seem like, you know, you did something terrible, your code's lost so much parallel performance improvement, but it might just not be avoidable because you're actually making memory accesses now. The best thing you can do in this case is to hide latencies. So, for example, perhaps you could be doing software prefetching, or if you had, in the case of the KNL, where we have 4 hardware threads per physical core, the reason that that is helpful sometimes is because if one thread needs data that it doesn't have yet, it can make the request. As the data is coming, another thread can jump in on that physical core and run and do some work. And that's a method of actually hiding some of the latency. You're keeping the physical core busy with these by taking advantage of the additional threads you have per physical core. So now I want to touch on some compiler-generated optimization reports. I find this to be extremely useful, maybe one of the most useful tools that Intel has. And you will have a lot of opportunity during the labs to work with this tool. So obviously the Intel compiler can generate optimization reports. There's 4 different components to the optimization reports. It can generate vectorization reports. Basically, this can tell you which loops are actually vectorized, why they were or why they weren't, if there's a flow dependency in there or something like that. It'll give you, actually, it's pretty cool. It'll even show you how far it unrolled the loop, like you were asking about before. It'll show you if it's going to be using the 8-width vector registers or restricting that to 4-width. It'll also show you where it has peeled the loops to get the data aligned, and also where there's leftovers from the loops, like if you've only got like 3 or 4 iterations left over that need to be done, not in a parallel fashion. It'll also show you where you've added OpenMP parallelization. It doesn't really give you much performance information about that, although some of the other tools that we talk about today will. It'll show you where your code has been inlined, which is great to make sure that it gives you the confidence that the compiler is actually inlined a given function that you're interested in inlining. And it'll also show you loop transformations that it does. So it'll actually, if you have nested loops, the compiler can reorder those loops, kind of has some heuristics in there that it uses to guide it, that'll either open up opportunities for vectorization or improve cache reuse. And it's pretty slick. So these compiler generated optimization reports are pretty easy to use, I would say. You know, you just do your compile line, as shown here, ICC x host to your vectorization, and then the flag qopt report. Qopt report equal 5. That's just the most detailed report that you can get. I think it varies from 1 to 5. 2 is the default, but I figure why not just get the most detailed one that you can get. There's actually, things are going to be broken up into 2 main sections for most code. You're going to get a section about the functions that were inlined, procedural optimizations according to Intel, and functions that are called that are not inlined are going to be marked with an extern label, and calls to functions that are inlined are obviously the inline label. Then you also get a report from the loop nesting, vector and auto parallelization optimization. So these are basically your vectorization reports and any loop modifications that were made. So what you can do, loop begin at vector.c, that's the source file where it's vectorized the code. 39 will be the actual line in the code where the loop occurs. And then it'll have some remarks past it saying what it's done to that loop. So for example, it's interchanged this loop with, it's interchanged loops 1 and 2, or this is loop 1 originally. And then it'll give me a message, this loop wasn't vectorized because it's not an inner loop, basically. Then it'll dump all kinds of vectorization information. So this loop starts at line 46. You could, it's not obvious what that is, but you can go and look in your source code and see, oh, line 46 is this loop. It's doing unaligned access to this particular array B. This is a peeled part of the loop. It's decided that vectorization isn't worthwhile here. And then you can look at the next one. This is the bulk or body of the loop, where it actually, in big bold letters here, it says in the middle, loop was vectorized. And what's kind of cool that I mentioned before is it'll show you the unroll factor set to 8, 2 lines up from loop was vectorized. And that's how wide it's using 8, or loading 8 data elements of each vectorization operation. It also gives you an estimate of the potential speed up down here due to vectorization. And then finally, you get some remainder loop stuff down here, which isn't usually a big deal. The most important one of these typically to look at is going to be the middle loop. Make sure that that was vectorized. That's going to be the bulk of the computation that's occurring during your processing. So I can take any questions about this, or we can move on to the next section. You will see all this stuff hands-on in the lab.
I have a question.
Yeah.
So you said vectorize or not, a compiler often can calculate the benefit and cost and decide balance. And, but I'm just wondering what happens if the loop iteration times n is decided in the runtime. How compiler can decide optimize and vectorize this loop or not?
Yeah, so the question is, if the iteration count of a loop is decided at runtime, how does the compiler know what to do? And the thing is, the compiler will make different branches where some branches, it'll make its little tests, and it'll be able to do that test at runtime, right? So if some dependency is introduced by the length of your arrays, you could say, okay, I can't vectorize here, but then it'll have an else part of that if-else statement that says, it checks it at runtime, and if it's allowed, then it will go through and use the vectorized part. But there's a little bit of overhead associated with doing that. But it is capable of doing that, yeah.
Does GCC have any optimization report?
I think it does.
Yeah, I don't know the flag, but yeah, they have reports. They're very similar to.
Yeah.
Yep. So, it's just like the normalized vectorization overhead is for runtime overhead, or
Where are you looking?
the normalized vectorization overhead,
Mm-hmm.
the runtime overhead? And is it in time or?
Yeah, I'm not sure how that metric is calculated.
Which one?
A normalized vectorization overhead. This guy right here.
That's all internal to Intel, and they don't want to say how they calculate it. So it's like the same, and you can guess what the scalar cost and all those things are, but they don't really tell you what any of them is. So it's just magic. You get the number and you believe it, and that's it.
But you could compare. You could compare the cost of doing scalar to the cost of doing vector, and if they're really close, then maybe you can do something to make it. Maybe that gives you some hint that, hey, maybe I could vectorize, set my code up to vectorize better. You might not know how to calculate these quantities, but they are maybe meaningful relative to each other. Just going to wait 2 minutes until 2:30 here before I start again. Okay, this will be the last section where I just stand up here and talk, and then hopefully for an hour and a half, 2 hours, we can just work through the labs together. But I wanted to give you a survey of 2 of Intel's tools that help you get performance out of your code on Manycore. And these 2 tools that I'm focusing on are Intel's vTune and Intel's Advisor. Now, I'll warn you ahead of time, these tools are extremely powerful. They can do a whole lot, but sometimes the interface and the amount of information they present to you can be a little bit overwhelming. So it can be, but you shouldn't be scared off from them because there are kind of straightforward types of information that you can get out of these. So I'll start with Intel vTune. It's basically like a classic line-level performance profiling tool. It's just capable of doing a whole lot of things. It supports serial, threaded code, MPI code, and hybrid profiling. Profiling with hybrid codes. If you're not familiar with the term hybrid, it's just when a code uses both MPI and threading. I would say that it does a better job with serial and threaded code than it does with MPI code. It loses some of its slickness when you go to MPI. One of the basic features it has is it can show you where you're spending most of your runtime in the code. Some of the more advanced features that it supports are based on the ability of it to actually sample from hardware counters at regular intervals, and then it can show you, correlate those places where it's doing those counting to locations in your code. If you're not familiar with what a hardware counter is, it's just a register in the processor that will record things like the number of instructions that have been run, the number of accesses to memory that have been performed, things like that, number of loads to the L2 cache. Now vTune, something that makes it a little bit, gives it a leg up over some of the other line level performance profiling tools out there right now, is that it has specialized support for the KNL, including information about accesses to the memory. So generally, you use vTune because it gives you insights into the performance of your code, maybe some ideas about how scalable it is, how well you're using the cache, things like that. I would say the analysis is simple and relatively convenient. It's a little bit more difficult to use in a environment like we have here, where we're working with shared nodes. A bit trickier than if you're able to use this on your desktop, it might work a little bit more smoothly. But you'll be able to decide for yourself as you're working with it later today. Like I said before, it's useful to look at memory accesses in particular on KNL. So all you really have to do to use vTune, you don't have to worry about this -L mem kind for anything that we're doing today. All you have to do to get all of the accessibility or activate all the features that you want in vTune is to compile your code with this -G flag. All that does is provide a symbol table that basically gives names to all of the functions in your code. So I can compile this first line ICC-G, blah, 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 and then at the end is the name of my executable. Or I could compile with MPICC and -G, and it'll give me the same kind of capability. Then you can run the program with what vTune calls its amplifier. And it has a graphical user interface and also a command line interface. And you access them through two different commands, amplexc-GUI, you can see the GUI, and amplexc-CL, and I can see the command line. And so you can run the program, profile it that way, and you can go ahead and analyze the results using either the GUI or the command line interface. This is how a job submission script might look like if you just wanted to fire off a job and have it profiled by vTune. If you have run anything on your systems before, you're familiar with the SBatch directives along here, giving various options about how long to run the code, etc. Then if you're running an OpenMP code, you're going to want to set your number of threads here. And then you would run your code a.out with the amplifier command line tool. You can collect different types of features, which I'll talk about and kind of dial in on what exactly you want, what kind of information you want out of that. Then this -R flag, that's going to determine the directory that your results get dumped into at the end. So this looks a little crazy. We'll see some simple examples, simplified examples of this, but basically the idea is you have some argument action, the action that you want to report, whether collect or report or get help. Then the action option, which that'll determine like what type of stuff you collect from. Then a global option, which will just do things like maybe suppress unimportant messages. Finally, the target to analyze, and then you can throw other options, which actually I'm not even familiar with what those might be. There is a link here. You're welcome to click on it now if you want. It'll take you to a place that shows you and explains all of the syntax for this command line component of vTune. So, yeah, vTune is going to be easiest to use if you're just doing one of these predefined types of collections. These collections have knobs, which are just additional modifiers that allow you to get maybe additional data based on a particular type of collection. And here's just some examples of how you might run this. The top one's quite simple, collect what they call hotspots. We'll go through what that kind of collection looks like. collect memory accesses is the next one. We'll go through what that looks like. And then this last one is maybe good to have in the back of your mind if you're running MPI code. This is the syntax that you would want to use. You would have all of your vTune-related arguments in the beginning, and then you call our MPI launcher IB_run, as you normally would, give it the number of processors, and then the target that you want to profile. And it'll be able to actually profile your code, even with that IB_run in front of it. So some different types of collections vTune has. Hotspots, this is kind of where you usually want to start out, and it's going to identify the most time-consuming parts of your code. You can do something called advanced hotspots. That gives you just additional information, like the CPI of different parts of your code. CPI is cycles per instruction, and it's some measure of what your instruction throughput is. How much time are you spent stalling, waiting for data or things like that. Concurrency will give you information about like threading synchronization overhead for like MPI. This guy, we don't have that working, so I won't be talking about it. Memory access will give you information about like how often you're accessing MCDRAM versus DRAM, how often you're accessing L2 caches. HPC performance, this particular collection is my favorite. It kind of combines aspects from hotspots for memory access along with some floating point information. Yeah, I'm not going to go through each of these options. The different knobs that they have here, basically, this analyze memory objects equals true. That's going to give you information about how much each of the data objects, whether they're arrays or whatever in your program that you've allocated, it's going to give you information about how memory access information about individual arrays, like how many L2 misses were there trying to get at that data. Analyze OpenMP equals true. That'll just help it'll generate some kind of information about inefficiencies in the OpenMP regions of your code. So if you wanted to run your job with the vTune GUI, you would do something like you'd fire up your GUI, go up to this quick analysis target thing, this button in the upper left, and you would type your binary into the first row in the center block labeled application. Tell it to run in the local machine. You would choose your analysis type then. So you click over one to get this particular window. And so you can see the different analysis types on the left-hand side. So you would choose one of those. And then you would just start, and your program will run and be profiled simultaneously. You can do stuff, you can do that through the GUI. I personally prefer to use the command line to do the profiling. But definitely for doing the analysis afterwards and exploring the data that you've collected, the GUI is a better way to go. So like you saw before, this is just an example of how you would launch the, or this is an example of how you would get a report dumped out on the command line, but it's going to be kind of this confusing jumble of text that will take some crossing of eyes and gnashing of teeth to decipher. So after you run something through vTune, it's going to generate a summary of the results. This will be kind of the first page that pops up when you bring up the results. In the upper first row, at the top, there's something labeled elapsed time. just the length of time that your program ran for. CPU time is going to be the time accumulated over all of the cores that ran. It'll give you your total thread count, and also the amount of time that your code was paused. The next line will show you the different functions in your code that you spent the most time in. This is pretty great. Actually, it shows you immediately the hotspots in your code. Now down below that is this CPU usage histogram. So this is on the KNL. There's 272 possible CPUs that you could be using 100% of the time. What this histogram is showing is the amount of time your code was running that the given number of cores was actually active. So this code, for 6 seconds of its runtime, only one of the cores was active. And then for almost maybe 9 seconds of its runtime, about 18 of the cores was active. Now, I don't particularly like how Intel has this labeled poor, okay, and ideal. Their idea that it's ideal to run on all 272 logical cores when there's actually only 68 physical cores doesn't really seem right to me. So really, I would not worry about the color of this in any of your analyses. Ideally, you are using all of the physical cores that you have, and so you would have a line coming up around 68 on the x-axis there. Now you can really drill down. So if I clicked on one of those functions that was a hotspot, it'll jump into it'll throw up the source code where that function is being called. And it'll actually show the percentage of time that was of your runtime that was spent in that function. And then you can even go from there. I don't know if this is necessarily the most useful thing, but it's pretty amazing. You can click on that line of code, and then it'll throw up the assembly that was used to generate that line of code. I guess I have actually used this before to make sure that a particular loop was using the vector instructions, the most advanced vector instructions available to it. So in that sense, when you can actually see the assembly, you know if your code's vectorized or not in a particular loop. There's also information provided, like I said, if you do a memory access analysis. So this is if I did a collect memory access. And what this shows, again, is there's some redundancy between these different types of collections that VTune can perform. So it'll show my elapsed time and CPU time. But what's pretty cool about the memory access analyses is that it'll give you an L2 hit rate. So that's the number of times that you try to load data from the L2 where it's actually in the L2. How well are you reusing your L2 cache? L2 hit bound and L2 miss bound are both metrics that kind of indicate the amount of time that you're spending, the amount of time that your code spends accessing the L2, whether it's servicing an L2 hit or servicing an L2 miss. In this case, the L2 miss bound was flagged because it's pretty high, and they give you a little helpful message about, you know, maybe what's happening here and maybe some way to fix it. You also get information about the amount of time spent in pulling data from MCDRAM and also from DDR or DRAM as it's called here. It actually gives you an L2 miss count below that, and things like MCDRAM hit rates, your number of thread counts, the bandwidth utilization histogram that it shows you. The x-axis is the gigabytes per second that it's pulling, and then The y-axis is the amount of time, amount of your runtime that you spent pulling that much data into the from memory. So this particular job spent about 9 seconds of its runtime. It was pulling 23 gigabytes per second out of the MCD RAM cache. This just has that broken down by channel, but you can see, again, it's just, you can look at the different individual functions themselves, see how many miscounts to the L2 occurred, what your L2 hit rate was in a given function, like insane levels of detail here. So talked a bit about the hotspot summary on a previous slide, but it's kind of cool. Is if you're running like an OpenMP code, it'll break up your runtime into things like okay, your effective runtime, but then it'll break out the amount of time that you spent with threads just spinning. Well, basically idle threads that are waiting for other threads to complete. So it's some idea of your load imbalance. So part of your spin time is going to be in balance or just serial execution. And then also part of that, I don't know if you're familiar with locking an OpenMP, but there's different function calls in OpenMP that enforce locking, which basically means that only a single thread is allowed to execute at some given point in the code. Then it also will give you an overhead time. And this is like the overhead time that we talked about of setting up your parallel execution region, and how much of that time is spent just setting up the parallelization and synchronization. And I'll give you your thread counts, etc. So that's pretty neat. We already talked about how this histogram works. You'll go through this stuff in the lab. This is pretty cool. So you saw these functions here. It's just the amount of time spent in those given functions along the top section. In the bottom section, though, you can actually see all the time that your OpenMP workers or tasks were actually doing something useful. That's shown in brown, and times that they were just spinning, and that's shown in red. And so you can just intuitively think like, okay, I want most of this to be brown. I don't want my tasks to just be spinning and doing nothing. And so you can look at this and see if there's any crazy imbalances amongst your OpenMP tasks. And so, yeah, we talked about you can drill down into the source all the way down to the assembly, crazy stuff. I've already talked about memory accesses with vTune, the memory access analysis. You can see this is a code that's accessing data at a very rapid rate from NCD RAM. Probably something like Stream is running. Oh no, this is LBS 3D, which is a code one of my colleagues works on. That's not good. Okay, so this is the analysis that I like. It really sums up, I feel like, the performance of your code. It adds CPU utilization and OpenMP information in the top. It throws in the memory access information. And then it also gives you how well you're utilizing the floating point units, whether those are vector processing units or whatever. It'll give you the upper bound of the gigaflops that your code achieved during its runtime. And then it'll give you a percentage or the amount of time or the upper bound for, it'll break that into scalar and packed operations. And so you can get a sense of how much time you're spending on scalar floating point operations and how much time you're spending on packed operations. We talked about OpenMP analysis, and one thing it does do is give you, it says parallel region time here. it'll give you some estimated ideal time that you could run the code in if everything was parallelized perfectly. Then some potential gain here, not very much in this case, 4.6%. Yeah, so we talked about all these guys. This is just a pretty neat view in HPC performance. These are all of your threads just packed together. And so if some of your threads were idle or something like that, you would be able to see that. So each one of these, it's a little bit too fine for you to really see. But basically you've got your threads number lined along the y-axis and then time along the x-axis. So we can see all of the threads are really quite busy as this code's executed. Green is good, right? Okay, so the basic VTune workflow, which like you'll be doing in the labs, is I'm going to compile with your debug symbols. That just involves throwing a -G at the problem during the compilation stage. You want to run the collection actually on the KNL itself with this, this amplifier command line, amplexc-cl. And then that'll generate some outputs, and then you can work with the GUI to analyze your results. So yeah, I'll talk a little bit about the advisor tool of Intel's. The idea is it's a vectorization optimization and basically OpenMP. Well, actually, it has all kinds of different types of threading that it supports, but it's a threading assistance tool. It says it supports serial threaded and MPI applications. I find that that might be the case that it can inform threaded and MPI applications, but you really want to be running it in a serial fashion. I think its role, at least as it's currently set up right now, it seems like it would be really good to run your code on your own, maybe desktop or something like that. And then this could give you some kind of advice about what kind of performance you could expect to gain by going to, you know, something like a KNL or a Haswell processor. So basically, some of the things it can do, it has kind of two different aspects to it: vectorization advisor and a threading advisor. It can evaluate the efficiency of your vectorized code and kind of help point out vectorized bottlenecks. It can provide incredibly precise trip counts, which is the number of times that loops get executed. It'll also give you the number of flops that were performed by a given loop. You check for loop dependencies for you, which actually could be pretty useful when you're parallelizing your code. And yeah, it can identify different imbalances within the operation of your code. The threading advisor will help you. You can do predict how your code's going to perform as you throw more threads at it using this threading advisor. And we'll see that we get the chance to do that in the labs. Yeah, it has these basic tools. The survey is kind of the first thing that you would run. It's actually pretty similar to the hotspots analysis in VTune. And it just kind of helps you find the places in your code to focus on adding parallelism. I am not sure yet what I think about the trip counts tool. I mean, it's just telling me how many times a loop gets iterated, which, yes, that can be important for very fine level optimization, but I wouldn't say that it's a first or second order effect. Suitability is nice. It helps you guess the impact of adding parallelism to what your code is going to be. It gives you some idea what adding OpenMP or going to a processor that has more cores on it might give you. Dependencies lets you identify dependencies before you parallelize. And the memory access patterns, actually, haven't used that yet. But yeah, I'm not even familiar with what that does exactly. This is the general workflow. It looks kind of complicated, but there's just kind of a couple of steps that you do when you're running this. You start at the top here, you build your app, you run it with Advisor. You can do a loop and trip analysis, run trip counts analysis. Then you get down and you investigate the loops. On the left-hand side, this is what you would do. It's kind of like the vectorization workflow. That's how it's actually labeled in the tool. And it lets you look very closely and get a lot of information about what would happen if you were to vectorize where your dependencies are. On your left-hand side is the OpenMP or multi-threading workflow. And this is going to be approaches to where best to add parallelism and how much improvement in your code to expect from adding parallelism. So how do we actually run this? First, you just set up your environment, module load advisor. You're going to export the number of threads. You want that to be 1. Like I said, you really want to run this advisor in a serial manner. Want to combine it, build your code with the debug symbols and whatever optimizations you're going to use. And then you just run this line down here. I don't understand quite why this -- search dir argument needs to be set in that way. But I have found that it does in order for this to work properly. And then you can analyze the data using, it also has a nice GUI associated with it. So this would be, after I run that, fire up my GUI, load my results, just kind of like in VTune. And this would be the information that it gives out for me. So under program metrics, it'll show you the instruction set that was used, number of threads. Then it'll show you, if you see the loop metrics right below that, it'll show you the amount of time that was spent in the vectorized loops and the amount of time that was spent in scalar code and a percentage of that time. That's pretty nice. Below that, it shows you the amount of efficiency that you gained in your vectorization relative to what you would have gotten had you not vectorized at all. And then it shows you the hotspots in your code. And if you included a trip count analysis, it'll show you the number of, basically it's the number of iterations through any given loops in your code. So that's under the summary tab, which is all the way on the left. And if I move one tab over to the survey report, it'll actually show me individual lines in my code and the efficiency that was gained, what the main type of operations that were performed there were. It's kind of like looking at the function level within VTune. It's very similar to that. Then in this bottom section here, if you were to click on the loop analytics, it'll show you information for that specific loop, number of seconds that it ran. It actually can break that down into the percentage of time that was spent on compute instructions, and the percentage, or rather the percentage of compute instructions that were issued versus the percentage of memory instructions that were issued. Like pretty crazy amounts of detail provided here. And just like in VTune, you can delve down into the assembly of given loops. There's some overlap between the capabilities of these two things. So I wanted to collect multiple types of data. What you always have to do first is do a survey run. Then after that, you can do some of the other runs. You can do a trip count run, as the second topic here shows, or you could do the suitability run. Again, suitability is how suitable a given, it gives you information as to how suitable a given loop might be for OpenMP parallelization. And it's not too bad to use, actually. You add maybe 3 lines into your source code, recompile, and then run with this suitability collection type on your executable. So I can see on the left here, it would look something like this. These are the 3 main functions that you would use on Fortran on the right. Those are the names of the functions. So if I wanted to do a suitability analysis on a matrix multiplication routine, like you see here, you can see the 3 nested loops in here, 2 matrices multiplying 1 row of one matrix times a column of another matrix, and then assigning that to the product matrix at the end. I want to see how this is going to perform with the OpenMP if I parallelize it. So what I would do is just add this line before the loop starts, annotate site begin. Then I would add annotate iteration task immediately after that. And then at the end of the loop, annotate site end. And so this will indicate to the advisor exactly which loop it is that you are working on parallelizing. By the way, if you are interested in any of the deep details of some of this stuff with Advisor, there's a link here which you should just be able to click on. It'll take you there. So if I run that annotated code through Advisor, this is what it'll dump out. It'll actually show me, so you can see this graph here, it'll show me what kind of gain I can expect to get in my serial code by using different counts of CPUs. This graph will adjust itself based on the settings I use in the middle here, the loop iterations tasks modeling settings. So I can adjust the average number of iterations from what it currently is to 5 times that number, or 25 times that number. And you can imagine that that's actually, in a sense, that's modifying the granularity of the problem, along with average iteration duration, the amount of time it takes to perform an iteration. So this is like playing with the granularity of the problem. Maybe I can add some more work into there in order to get a better parallel efficiency or better gain in parallel operation than I currently have. And then in the end, you replace this with whatever you decided. Pragma, OpenMP parallel for loop. This has now been parallelized. Like part of the reason that you wouldn't just start off doing this, I think, is if you were testing this stuff out on a machine other than where you were going to run it on, right? It gives you the capability of figuring out how well your code is going to scale to larger numbers of cores that maybe you have to be able to run your code right now. Yeah, I mean, what it can't do, it's really designed to analyze serial code. Doesn't catch every single problem. It's still a relatively new tool, actually, and they're still working some of the kinks out of it, I believe. Yeah, these are just some references that will provide all kinds of like the tutorials here might actually be quite useful for getting a feel for how these tools work. But with that, we're going to wrap up the tools section, and you'll get a lab where you get to work on these. But we're going to start off with a lab where we look at optimization. Optimization using things like compiler reports as opposed to optimization using VTune. So just like before, y'all are gonna want to SSH into the login node on Stampede, enter your password and token, then extract the lab for this section. It's going to be KNL opt train. Start an IDEV session while you're there. One thing that you might find convenient is to give it this -m flag. If you tell it 60, that'll get you your session for 60 minutes. The default is 30, so it's convenient to grab one for 60 for this lab, because it might take about an hour, I think. And then just hop into the directory. And then from there, feel free to just work your way through the lab. I think there's 3 exercises. And flag us down if you need any help, or if you have any questions, we're here for you.
So for when we schedule the then the number of threads is spawned with the same number as the number of chunks.
No, so your number of threads will be set by the OMP num-threads variable. In your, like you do that before you run your program, right? Set the number of threads. That'll be how many are used throughout the program. There are function calls that you can use to change that in the program, but we haven't talked about that in this section. It's actually probably a good thing to cover. What that'll do, the dynamic, is by default, it'll take an iteration, give it to this task. At the same time, it'll take an iteration, give it to another task, and might just dish them out that way. And just try to keep every task as busy as it can. If you specify a chunk size, rather than just handing out one iteration at a time, it'll hand out that number of iterations. So if I say 50, it will hand out 50 iterations to each task when they come back and ask them for more.
Then if we know the number of threads, which is optimal by VTune, then we should set that number of threads like for OMP thread based on the VTune.
Yeah, well, so VTune won't really tell you, right? Advisor tries to. And Advisor is a good guide, but it's always good to check and just run it yourself, even if it's like, just for a tenth of the runtime of the code or something. So it's good to just time the stuff yourself too, to be sure, and adjust the number of threads that's being used. It's always good to play with that and scale it. and not just rely on some of these tools. They kind of, the tools can kind of point you in the right direction, and then it's good to really do it by hand, in my experience.
And the number of, optimal number of threads for OMP block, not whole program, and then set each number of threads which is optimal for each block.
Yeah, so that's what the site annotation stuff was that I was talking about at the end with Advisor. That's looking at, you can adjust the number of threads for that particular block and get some idea of how the parallel performance will behave as you increase and decrease the number of threads. That allows you to do the at a block level.
Another question, OMP thread is, once OMP thread is scheduled to some hardware thread, or that is not scheduled by the other thread until that OMP thread is finished the job. So that if there is any synchronization event, they just spin off and other thread not scheduled by the thread by OMP.
If it is static, yes. If it's dynamic and your other threads are doing work and this one's finished, they will toss some of their work, they will pass some of their work to the thread that's not doing it.
So I mean, each core is still doing some time slice scheduled by operating system.
Well, if it has no work to do though, it's not. It's just sitting there spinning, waiting for the other threads to finish. Now, while it's sitting there, can the operating system also schedule something else there? I don't think so. I think it has to keep spinning because it needs to know as soon as it wants to be low latency. As soon as those other threads are done, tell it it wants to be ready to go. It wants to be able to release that resource. But until they complete, he has to hold on to it. But I don't know. I think that's how it has to work. I don't know for sure with hardware threads and everything how they have something to test at this point.
And then for the hardware threads, they are actually scheduled for 24 or they are scheduled 1 and 2.
As far as the operating system is concerned, they're simultaneously scheduled, but the hardware kind of just lets each one go when when one completes or one has to wait. It'll just let another one go.
So in hardware, it is actually scheduled one by one. Of course.
Yes, yeah, because they have to share. They all share the execution resources of that core. The operating system doesn't really know about that.
So for MPI, they may use multiple nodes, and then if I use VPN, then the result is aggregated result from multiple nodes, or each result is called.
Yeah, what will happen is each node will have its own result. So it doesn't aggregate. Have to just open each one individually. Hopefully, they're all behaving in a similar way. Now, if you want to look at things like imbalances between nodes, what's the Intel MPI thing called? ITAC?
Trace analyzer.
Trace analyzer? Yeah, there's a tool called Trace Analyzer that's installed on our systems and help you with MPI codes.
Not more.
Just a warning. So no, you didn't wrong. This is, I'm just saying, file the data. Yeah, so that second step there, you'll get a warning. Hey, you can look at this private, but it's just a private. So the compiler can run. Okay. I just want to warn you that it doesn't know what to do with that. It's not to pay attention to it. When you do compile with OpenMP file, it will. Maybe, yeah, a little unfair. Yeah. Now, I'll make one point of clarification for anybody following the labs online. Exercise 1, step 2. You should expect to get a warning, and don't worry about that. It's not a problem. It's just a warning.
I missed the beginning. I was busy with retooling how to put. Why is it slow? Why is one thread with OpenP slower than the other?
So check it out to figure it out.
No, I need the shortcut.
Look at the optimization.
So it does it does some loop interchange when you do OpenP.
No.
When you don't. And why doesn't it do? Oh, with OpenP you can do it, yeah, sure.
It has to respect.
Oh, what a contrived example.
Oh, come on.
Okay, now I get it.
Oh, this is something you could run into when you
Yeah, if you're parallel, if you're how to do this, but the right. But I can change that. You add an OpenP collapse. Where you can, in OpenP can collapse, you can join two loops together.
Really?
And if you interchangeable loops are the outer two loops,
See,
and you do a collapse, then OpenP can do that.
that's way better. See, I talked about combining loops, but you know that. So we gotta add that.
Yeah. So if your outer loop iteration is 50 and your inner iteration is 50, when you do collapse, then you have 2,500 loop iterations, and then you can have more threads.
Yeah, I'll need an expert. Second.
Yeah, I think Hack is too expensive. No, but that is a tricky example. I couldn't figure that out myself. But yeah.
No, it's weird.
Yeah, if you just interchange the outer loop, and if you make that one open P first.
How's the online looking? People losing their minds, rioting. Okay. I don't see any questions specific to the next set of labs. Refresh the page and see what
Are you tweeting? You're having too much fun. My goodness. Super glue.
I think we should make the online so it's not distracting or
Yeah, should be fine.
then we could actually you know in the presentation, I mean, because we're not going over any new material, but you want to keep that conversation. Let's get the we should get the Ethernet. I would had
Yeah, we'll keep the Ethernet.
Carlos and still active, so we can just post a note in the Etherpad or terminate the session because there's no more material. Right. Then I can use the Etherpad thing too, which I can right now. So, yeah. Go ahead and just do that.
Do you have another exercise of this, or do you have, is it then tools?
No, there's two of these, or
Okay.
three of these total.
Okay, I wait till the third one, and I have to write this email to Rico. Okay. For a tool.
Which one's that for automatic parallelization?
Yeah, and then there are multiple. I am losing track, but we look at something. Came up with some stuff we could make better.
Nice. Yes, exactly. We are running. We'll try 272. 272. Okay.
I mean, there's no guarantee that hyper-threading gives you better performance.
No, but in my testing though, in this particular case, it did.
Oh,
And,
I
yeah.
understand that. The thing is that, I think you like, you should kind of have it.
Yeah, I don't know. Mhm.
How many iterations do you have? 2,000, 10,000? Yeah, like the.
Yeah.
It's kind of like 1,000. Yeah, sure, I'm running with 20,000.
I wonder if I did have by accident.
Yeah, right now.
I mean, if you have 100 threads and you do 2,000 loop iterations, then if it is imbalanced, you can already lose 5%. Because 100 is 5% from 1,000. And that's a low number of iterations compared to the number of layers.
Yeah.
Um,
They could do like agency.
What I was seeing, when I was using more threads, back there, it's going faster. And I assume this is just.
But try 100 iterations.
I think I didn't write this.
Just before we close it out, you mentioned showing. Do you have a slide that's
I can just throw up a notepad.
Yeah. So, it's a little bit bad. So we just, if you don't have enough.
Turn on screen share.
Then the worst case is we have 9 iterations and 8 threads.
Yeah.
But if you do, if you have 68 threads and 2,000 loop iterations, you can already lose 8% at the very end. So, just one over. I think
I can just do.
What is 2,000 divided by? 39.5.
Stop yelling at me.
But if you use 130 threads. Then it's looking for, doesn't make that much sense. But if your number of iterations is only 10 times of the number of threads, then you already and you are already. And you only the thread, but then each thread has only a few iterations. It makes sense. Makes sense. And you can, just for giggles, try 272.
Oh, I have to do something to share the screen again, right?
Green on my.
Yeah, that's. Sure. Or you do divisible by 68 plus 1. Then you should get kind of a maximum non-benefit. That's, it looks like more than 30 seconds. It feels like it. No, we got a better result with But we get a much worse result with 272.
Oh, you know this example?
Okay, I guess we definitely know it's lower. And another effect where you can lose performance is of course your relative cache size shrink. Sure. And that could be recovered here because I think your interval is at 10,000. So that's basically something like
So
infinity 4 kilobytes.
and the one without
I
open
guess.
is
And
interchangeable.
the level 2 caches of the
Well,
order of
when it's
64. You divide 64 by 4, you already have 16, you have more than one array. It could be that you're just outside the level of section. Yeah.
What is it people that make that? The result right now is 18 seconds.
Yeah.
Four times larger, so it's right. It changes the.
Yeah. Maybe. Keep it up. At least, often we write these little test codes and there's not that much to see. There's always a happy to see that.
Oh,
We can
no,
really
okay.
actually make it that much slower.
Watch out.
Oh, yeah. You'll be happy to do everything much slower.
You choose it to two.